All right, so let's start at Unit 6 Solutions, and we're going to begin with looking at how things dissolve. That'll be the title of 6.1. First, let's talk about what makes up a solution. There's some important definitions that we have to understand here. The definition of a solution is a solute that's dissolved in a solvent so that the homogeneous mixture is formed. And so within that definition, there's some other terms that we should probably point out. So solute. The solute, I'm just going to say, that's the stuff that's dissolved. And the solvent is the liquid doing the dissolving. It doesn't have to be a liquid, but we're going to talk about liquid solutions for the most part. And so that's why solvent is defined as the liquid doing the dissolving. I have the word water in parentheses because more often than not, water is going to be the solvent we care about. And so here's a little diagram of a solute, the orange dots being dissolved in a solvent, the clear liquid. And remember, this forms a homogeneous mixture, so it looks the same all the way throughout. So why does this occur? Well, we actually have to take this in two steps. First of all, we're going to talk about ionic compounds, and then we're going to talk about covalent compounds. So just to refresh our memories, ionic, it means we've got a metal substance that's bonded with a non-metal substance. So a metal thing bonded with a non-metal thing. My model on the right-hand side of the page is looking at sodium chloride. So there's chlorine ions, those are the green ones, and there's sodium ions, those are the blue ones, or the purple ones, whatever you want to call that. So what happens with an ionic compound is the atoms that make up the grain, if you want to think about this green and purple conglomeration on the right side here as being a grain of salt, when ionic substances dissolve, the atoms that make up that grain dissociate into their respective ions. And I've got that word bolded, dissociate, because it means to break apart or to break up. If you dissociate with somebody, that means that you're going to break up with them or you're going to just totally not talk to them anymore. You're dissociating with them. And so that's what ions do when they're in solution. And so what actually occurs, we'd have sodium ions, so that'd be a sodium atom minus one electron, and chlorine ions, so it'd be a chlorine atom plus one electron that are just floating around in solution. So they're breaking apart like that. Why does this happen? Well, dissociation is actually caused by water's polarity. In the first semester, at least in my class, we talked a bit about the polarity of water, and I want to kind of draw that to start out. Water molecules, if you remember, they don't have just a straight line shape. They're actually bent a little bit, and they're bent because of that concept that we talked about, VSEPR, valence shell electron pair repulsion. If that is not familiar with to you, please ask about that in class tomorrow. So if the water molecule has this type of shape, most of the electrons are actually going to reside, again, around the oxygen atom. And so the electron density, as we'll call it, is going to be around this atom right here. That's why I'm circling in green. And so that side of the atom, if you think about, or I'm sorry, that side of the molecule, if you think about this entire thing as being a box, the top side of the box is going to have a stronger negative charge. The bottom side of the box is going to have a stronger positive charge. And again, the reasoning is because those electrons are going to be primarily around the oxygen atom. And so if we were to cut our molecule in half, our water molecule in half, and most of the electrons are up top, you see most of the green circle stuff is up top, that means most of that molecule is going to be negatively charged up here, where again, most of the bottom half of the molecule is going to be positively charged. So that's what I mean by polarity. So one side is negative, one side is positive. All right, so to move on, let's get through that. Let's take a picture of what would happen if we could see atomically if water molecules were surrounding chlorine. Well, you'll notice that the hydrogen atoms, which are the blue ones, are close to the chlorine ion. And if we take a look at sodium, you'll notice that the oxygen atoms, which are the orange ones, or the reddish ones, are close to the sodium ion. And this whole concept, this dissociation, this ability for the sodium and the chlorine to break apart from one another, is solely based on the fact that the affinity or the attraction of the chlorine to the hydrogens is greater than the chlorine to the sodium ion. And so that's why the ions are going to break apart or dissociate. Now we have to make that distinction that that's only for ionic compounds. Covalents do something a little bit different. So when covalents dissolve, and remember, covalents, chemicals, all nonmetals. Okay, so no sodium or magnesium or iron, no. Covalent compounds have all nonmetals in them. So they dissolve because the molecules that make up the grain, again, if you want to think about this big purple blob in the lower right-hand corner as being a grain of sugar, the molecules that make up the grain dissociate into actual separate molecules. So they don't break apart into individual ions, but instead they break apart into individual molecules. So a grain of sugar is actually a whole bunch of molecules stuck together, and this picture does a really nice job of showing that. So we've got all of these molecules that are stuck together, okay? And what happens is the water will actually pull those molecules apart. It'll say, okay, I'm going to take that molecule, and you take that molecule, and you take that molecule, and you take that molecule. But the molecules, the ones that I'm circling in red, they keep their form, okay? So there's multiple sugars, but let's just say this sugar has 2 carbons and 4 hydrogens and 2 oxygens. And so that purple hexagon, or that sugar molecule, will stay C2H4O2. It just won't be combined with any of its buddies anymore. And because the water is pulling all the water molecules apart, it becomes harder and harder and harder to see the grain of sugar, and thus it almost appears to disappear. And that's why things dissolve. So again, the sugar crystal is the purple hexagon, and remember that purple hexagon is C2H4O2. It's not like we break into individual carbons and individual hydrogens and individual oxygens. It's individual molecules. So the big part here, the carbon, hydrogen, and oxygen actually stay together. Okay, so that gives a reason or an overview of why things dissolve. Now we're going to talk a little bit about how one thing can dissolve another thing, which leads us to our guiding question that we had in class today, which was, why do some things dissolve yet others do not? So we got to look at a big picture here. So solutions, the reason they form is because of the attraction between particles in solution. And so if we're talking about particles in solution, we might talk about like water molecules and sodium ions. It's the attraction between those two things that allows this salt to be able to dissolve. If that attraction doesn't exist, then solutions just simply will not form. And so in order for that attraction to exist, substances must have similar polarities. Again, I talked about polarity with water in the previous slide. They must have similar polarities in order to form a solution. So water is polar. Ethanol, as we'll look in class tomorrow, is polar. There's a bunch of polar compounds. You put polar compounds together, and they're going to dissolve one another. Okay. Let's take a look at what this looks like using some models. So water and sugar. We're going to focus on water and sugar first. You're going to notice the water molecule, again, having the hydrogens in white and the oxygen in red. The water molecule is polar, and that polarity is actually signified by this little arrow right here. That's showing what we call the molecular polarity. So what I mean by molecular polarity, that's the polarity throughout the entire molecule. So we've got, again, an oxygen, a hydrogen, and a hydrogen. The top half of that molecule now is positive, and the bottom half is negative. So the overall molecular polarity, we've drawn these arrows before, these dipole arrows, looks like that. It's pointing straight down. And so that's the molecular polarity. Sugar also has a molecular polarity, but it's a bigger molecule, so it's a little bit more complicated. I'm not going to walk you through how we know its molecular polarity, but its molecular polarity is present. And so half of that molecule is more positive than negative. So sugar and water both exhibit this concept of molecular polarity, so guess what? Sugar and water dissolve. And that brings me to kind of the title of this slide, like dissolves like. Does this guy have molecular polarity? Yeah. Does this guy have molecular polarity? Yeah. And so what does that mean? Well, that means that these two will certainly dissolve. Okay? Now let's look at the other two molecules that are on the page, oil and benzene. Well, oil could be any type of oil, maybe vegetable oil or oil from a car. And if you look at an oil molecule, it's very symmetrical. That's one thing that you should notice. It's very, very, very symmetrical. So what I mean by that is if you cut the molecule in half, you're going to notice that the side on the left is very similar to the side on the right. So the red side is very similar to the green side. Likewise, if you're able to cut that molecule this way, you'll notice that the bottom side of the molecule, very similar to the top side of the molecule. Actually, it's identical. And so this symmetry gives rise to something called nonpolarity. And what you'll notice here in my little yellow bubble is there's no arrow. So that means there's no pole. So this substance is defined as being non-polar. And you can use that same concept to look at the benzene molecule. Okay, the benzene molecule, if you cut it this way, same on both sides. Cut it this way, same on both sides. And so the benzene molecule is also non-polar. And remember the title of my slide, like dissolves like. So if you take some benzene and you mix it with oil, those two things, they're going to mix together. Now here's the thing. What if we take some oil and some water? Will they mix together? Well, obviously they won't. We've seen this in the chocolate lab activity, and we've seen this in daily life. And the reason they don't is because their chemical structures are too different from one another to actually mix. So which will form a solution? We know the sugar water will, the oil and the benzene will as well. So then to quickly relate this to the chocolate activity, I've got 4 molecules up here, and all 4 of these molecules we dealt with in the chocolate activity. Here we've got one of the molecules that would be in butter. Butter is actually a mixture, but this is one of the triglycerides that would be within butter. And here we've got one of the molecules that would be in vegetable oil. And we can see that those two molecules are very similar to each other. In fact, they have a very, very, very large area in the back, which we would call nonpolar. That nonpolar area, because it's similar in both of the molecules, allows those two things to melt in each other. And so you saw this with the cocoa butter and the vegetable oil. You guys saw that as you kept rubbing that for about a minute or 2 minutes, that it started to break down and get smaller and smaller and smaller. So the cocoa butter, the CB, and the vegetable oil, the VO, actually mixed. I don't have to go through the water and the sugar because you saw that, so the water and the sugar also mix. Okay? But we know that the cocoa butter and the water didn't mix, and we know that the vegetable oil and the sugar also didn't mix, and that's because their structures are too dissimilar. So one thing we'll talk about at the beginning of class tomorrow is the whole chocolate and gum gross thing that you did at the end of the experiment, and why is it that the chocolate actually destroys the gum. All right, a little long for that video, but I think it hit everything that we're really looking for. Okay, that's it.